This section from the Larson book is more graphs and displays. Now, the first type of graph we're going to look at in this section is called a dot plot. Dot plot is very easy and can have some useful applications. Anything that helps display data in a visual manner is always helpful. I don't think we have to spend too much time on this because in a dot plot, all you do is kind of put the range of values of your data on a number line. Now I kind of skipped all these intermediate points from 8 to 20. And when you have a data value, such as 2, you put a dot above the 2 on the number line, and anytime the value repeats, you just stack that dot on top of it. So we'd go 2, and then put a dot for 4, and then another dot for 2, and the dot for 2 would stack right above the other dot that was there. So this can show you, this was a very small example, but it could show you, trends where maybe data was heavier at a certain region than others, and heavier meaning more values. Anyway, let's talk about something called an outlier. An outlier is a value that's far removed from your other values. Now, there's certain ways you can kind of determine an outlier, and we'll look more into those actual ways later, but I think for the most part, it's just kind of important to understand the concept of an outlier and what it is versus a precise calculation. So sometimes you can have dot plots and have questions about, either constructing a dot plot like we basically just did, or answering questions on an existing dot plot or one you constructed. Like perhaps for this one, this says what proportion of the values are less than 4. All right, we have, you can go back and count the total number of numbers, but you have 16 total numbers in that list, so that's your denominator. And how many are less than 4? Less than 4 would include all dots 1, 2, and 3. So there's 2 dots, 4 dots, then 1 dot. So you have 7 dots total. So 7 out of 16 are less than 4. And that could be converted to a percentage. So it's just however the problem wants it addressed or whatever, fraction, decimal, percent. But it would all be the same idea. More than 5. Now you got to be careful with this one because it'd be real easy to make a mistake to only count the 6, 7, and 8. 1, 3, 1 makes 5, but your outlier way out here is greater than 5. And 6 out of 16, I did not reduce that fraction. Didn't need to really for this purpose. So yeah, watch out for those outliers. One thing I want to mention about outliers, they don't have to always occur on the larger side. You could have a set of data and the outlier could be at the low end. Stem and leaf is another way to display data. This one's a little trickier than the dot plot, but once you get used to it, it's not too bad. Don't worry about this key thing right now. I'll talk more about that a little later. But on a stem and leaf, in this case, the stems represents the tens digits, and the leaves represent the ones digits. Now, we didn't need this frequency diagram, but I will refer to that in a minute. So if you look at your data up here, 12 and all these numbers, and there's 41 on the next row, the way we do this is you take, so we know we're going from anywhere in the tens range to the 40 range. So that means our stems would be 1, 2, 3, and 4 to represent multiples of tens. Now the leaves are the ones digits. So for 12, we put a 2 in there for a leaf. The 2 goes with that 1 to make 12. So 1 with 2 makes 12. Now for 13, we put a 3 in there. 1 with 3 makes 13. So you see those leaves don't interact with each other. Every leaf goes with the stem. So the next one, 21. 2 with that 1 leaf makes 21. 2 with the next leaf, 7, makes 27. And then 33 would be 3, 3. 34 would be 3 and 4. 3 and 5 is 35. 3 and 7 is 37. any number that repeats, because it is a data value, so it doesn't just count once. So the fact that I have two 40s there means I need two zeros to represent both those 40s, and then the 1 for the 41. It's often asked, do these leaves have to be in numerical order? Well, for the most part, they're usually presented in numerical order. I guess you could argue that they don't have to be, but I think it's best if you put them in numerical order. Now, this once again is a small data set, but this can also show trends and patterns. You can see how far leaves stick out, or you could sort of, if you imagine this stem and leaf tilting over to its left 90 degrees, then you could see the leaf sticking up. It would almost look like a frequency histogram that we looked at in the section 2.1. So they're just kind of anything to show patterns. Now the number of leaves then tell you this. We didn't need this frequency diagram, but the 2 frequency meant there are 2 leaves here, 2 for the next one, there's 2, 4 leaves here, 3 and 3 leaves there. Let's come down here. Now I'm going to mention real quick now what the key kind of represents. Now the key, you don't really need a key if you have the actual data. If you have the actual data, you don't need the key, but the key is there in case, stem and leaves could be done with decimal values. So let's say that these were going to be decimal values, like you wanted the 2 with the 1 to be 2.1. The key would just then be written 5 bar 8. That's not divided by, it's just a bar, that's the same bar that separates the stem and the leaf. So it's like saying 5 with 8 would be 5.8 if we wanted the numbers to be decimal. So it's not that big of a deal. So that's the reason why. But if you see the numbers, like in this example right here, you can see that they are not decimals, right? So you don't even need the key. The stems are going to be multiples of 10. Now here's something very important. Well, the stem and leaf diagram did not show up in the last example. So now these aren't sorted, but you can identify here that we're going anywhere from the 20s all the way up through the 80s. Now it's very important that you list consecutive stems from 20s to 80s. 2, 3, 4, 5, 6, 7, 8. Even if there are no leaves in that stem, they need to all be listed, because that gives a better visual representation of the data if you don't skip any stems. And I intentionally created this data so there would be a couple of them would be blank. So all of them have to go 20 through 80, and then same pattern. So I won't go through all these again, but so like just the 21 there, see there's 2 21s, so there's 2 leaves there that represent those ones, so forth, so on. Yeah, there's 3 7s there, so evidently we should have 3 27s. Yeah, I see them. 1 here, 1 here, 1 there. Now 40s, there's some 30s, there's no 40s, so you don't put a 0 there, obviously. You just leave it blank. Because if you put a 0, that means you're saying the number 40 is there, and that's not true. So here are a few numbers in the 50s, 60s. There are no 70s in this list, so I leave it blank. And then 82 and 88, the last two, we have a leaf of 2 and a leaf of 8. All right, so very important that you list all stems from lowest to highest, even if they're empty. Now here's one where you're kind of given a stem and leaf. So I'll put the key here to indicate that these weren't decimal numbers. They are. So you can have multiples of 10. That just represents hundreds. Where it's 10 times 10 is 100. So 10 with 2 just means 102. So let's say you're looking at this stem and leaf, and it's asking what's the maximum and the minimum values on this. All right, go the smallest stem and the smallest leaf. That's why it's probably a good idea to keep these in order. 10 with 2, that makes 102. You go down to the largest stem, which is 13, and the largest leaf with it is 6. 13 with 6 makes 136. And here's another proportion question similar to the dot plot. What values are less than 20? Now you don't have to rebuild this entire list. We don't have to list out all the data like up there. All you got to do is count the number of leaves, because the number of leaves tell you how many data values there are. So anything in the 10 or 11 stem row is going to be something less than 120. So the 11 has 2 leaves. The 10 has 5 leaves. 7 leaves means there's 7 numbers. So it's 7 out of 18 total. And you can obviously count the total. The total number of leaves tell you how many data values there are. So you did not have to rebuild this list from scratch. And let's just mention what relative frequency. That's what we're kind of doing here is relative frequency. You want to summarize what that is. It's the frequency, the number of items, and divided by the sum or the total number of items. Now here's an example with, let's say we surveyed 200 people and we only gave them 5 automotive choices, not any car they could pick. Which out of those 5 is their favorite? So this is a frequency distribution now where we're using qualitative data, not quantitative. So we don't have numerical here. This is strictly qualitative. And so I just made these numbers up, but obviously if there's 200, I had to make sure they added up to 200. And then the relative frequency, that's you just take each value and divide it by the total. So you see I wrote it as a fraction, I wrote it as a decimal, and I also wrote it as a percentage. You know, they could be in any of these formats. Not likely all at the same time, but I just did it to show you all of the formats. And that brings us to what's called a frequency bar chart or a percent bar chart, or just I call them regular bar charts. Unlike the histograms, with the histograms are a special bar graph. You know, they have to be vertical. The bars have to touch. They're based only on quantitative data. This can be used for qualitative data. The bars don't need to touch. They can go sideways. They can go up. If I zoom in here, like this one going sideways, so I'm taking those frequencies from over here. I use Microsoft Excel to plot this, but if this was already plotted, it's not too difficult to read. Of course, then, but you know, reading the exact answer could be a little challenging here because there's no intricate values there. But you can see it's pretty reasonable. So the Honda sticks out close to 60, and it's 58. There's the Porsche right at the 30. BMW's at 28, just under 30. Porsche 30, Mercedes 32, and then Toyota is at 52, just over the 50. So there it is sideways. Here it is vertical. I even did them as percentages down here. I just let Excel do it as a percentage. So you see it has the same shape. So you just, however the other, you know, one axis in this case is just qualitative word data. So there's only one numerical axis here, whether it's horizontal or vertical. But whether you use percentage or whole number frequencies, it's going to display the same shape. It's going to give you the same idea. It's just using different numbers as a reference. So that doesn't affect the visual portion of the graph. Pie charts. A lot of you may have seen pie charts. They're very commonly used to represent percentages of data. That way you put everything in one circle. That adds up to 100%. So you're not going to have to worry about your ability to construct these pie charts, just how to read them and interpret the information given to you. So you see, I took that data from above and used Excel, and there it is, broke it up into, shows each of those percentages from up here. Obviously, it's those decimal values multiplied by 100. And now suppose we did not have that other data up there and you were only given this pie chart. That was it, with these percentages. And then it says, suppose we had 600 responses. How many people chose Mercedes? I just picked that one as a choice, as their favorite. So what you're trying to figure out is you're trying to say, okay, some value X out of 600, it's a relative frequency basically, would equal 0.16, which is 16%. Long story short, you don't have to even write that equation. All you have to do is multiply your grand total, in this case 600, by whatever the percentage is as a decimal. So 600 times 0.16 for Mercedes gives us 96. Had they asked Toyota, you would have done 600 times 0.26. So you just make sure you multiply by whichever one of those it's asking in the question. So long as you do that, this should be very easy. Here's another one. Sometimes when you multiply these, they may not come out to be an integer answer, but obviously the answer has to be. So just round to the nearest whole number. This is not like the class width stuff in first section 2.1 where you must round up. This is normal rounding to the nearest integer. So we have these percentages, and then they're kind of color coded up here. So out of 477 students, about how many were business majors? So you multiply, which is the purple here, 477 times 31.31. That the squiggly means approximately equal, so that answer is not exactly 148, but if you multiply it, 148 is going to be the closest value to that. So you would just pick 148. So if it doesn't come out to be the exact integer, just round to the nearest integer. But it has to be a whole number. Now here's one where it just gives us the bar graph, no totals, and all it tells us out of these how many, what percent of these use Sprint as their provider. Now this one's I think is easier to read when it's between the lines, because you can see how, unlike the ones where it was going by tens earlier, that's a little trickier. But so like for example, if you're going from 8 to 10 and it stops halfway short, the only integer between 8 and 10 is 9, right? So that has to be 9 right there. So I said 9 divided by 37. Now, I wonder how I got 37. Where'd that come from? Okay, well, they didn't tell you the total was 37, but showing you this bar chart, we can get 37 because all we have to do is add up the frequencies for all of them. So AT&T had 10, Verizon had 6, T-Mobile had 8, Sprint had 9, Vonage had 4. Add those up, as it says here, the sum of the frequencies, you get 37. So you take 9 divided by 37. I just use 24.3%. Your exams are going to be multiple choice, so you just have to pick the right answer. So the rounding is not that critical. You'll be able to, if you do it properly, you'll be able to identify the answer easily. Now, since these are percentages, they don't have to be whole numbers. So I don't know if they'll round to the nearest percentage or use 1 or 2 decimal places. This is just something I kind of want to show you. I don't want to spend a lot of time on this, but how sometimes you can be misled with charts and graphs. Doesn't mean you're being lied to. It doesn't mean the information is wrong, but it's how it's presented can be a little tricky, and that has to do with how you scale an axis or something. This is I copied this from somewhere, so the fact that unit of measurement is British pounds. So wherever I got this from, this is in pounds. So they're trying to make a claim where it says massive increase in house prices this year. So you look at that from 1998 to 99, you look at those two bars, and it looks like it's like over double, doesn't it? Just the shape of the bars, the size of the bars, like, wow, it's almost doubled. But it has not. If you look at the y-axis, it's just gone from 80 to 82. So you come to the graph to the right, scaled a little more normal, you see that 80 to 82 is not really that much of an increase. So they weren't lying over here. It went from 80 to 82. That's correct. But they tried to trick us on the y-axis by not starting at, by not scaling. You see that gap from 0 to 80,000, and then from 80 to 81 is the same gap. So how they scaled the y-axis gave the bars a different shape to give the effect that they wanted. Now, I can't quite tell what they were trying to accomplish with this graph, but the same thing here is, the axis is, you see it goes 0, 1, 1 to 2, which is fine, but then it goes 2 to 4, 4 to 8, and you see they're all equally spaced, and it's doubling. Whereas here they spaced it out evenly to give a true representation of what the graph's supposed to look like. So I'm not sure what they're trying to show here. And I just kind of mentioned it. Bizarre vertical scale. All right, so that concludes this section.